Hello, everyone. So today we are glad to have Professor Stephen Su to give us a talk. Professor Su is from the Department of Physics and Astronomy in the Michigan State University. He receives his PhD from the University of California in Berkeley in 1991. And then he was a Harvard Junior Fellow, as well as Superconducting Super Collider Fellow from 1991 to 1994. And today he's going to tell us about the famous, or rather infamous, paradox about information loss in black holes, and then about your proposal on how to resolve this using quantum hair. So without further ado, please, you can begin your talk. Thank you.
Great. Well, it's a pleasure to be speaking to you. I'm sorry you had to get up so early this morning. I'm going to share my screen with you now. Can everybody see that?
Yes.
Okay. So the topic I'm going to talk about is both famous and somewhat specialized. So I'm going to go through some introductory remarks so that everybody can follow. And if you have questions, just let the organizer know and he'll let me know. You can ask questions at any time. You don't have to wait till the end of the talk. So the work that I'm going to talk about today is done in collaboration with these authors, Calmet, Casadio, and Kuipers. It's based on two papers that were just recently published, one in Physics Letters and one in Physical Review Letters, just in the last few months. The slides for this talk are available. You can get them from me or you can get them from the organizer. The links on this reference page are live. So the line that says colloquium, black holes, entropy and information, that is an even more introductory talk. It's actually a colloquium on this topic, which introduces the basics behind black hole entropy and information. So if you get the slides and you click that link, it'll go to another talk. Two review articles that I recommend are the following. One is a recent physics reports by Surat Raju. And Raju and his collaborators have worked on a research problem which is very complementary to what I'm going to talk about. They worked on something called information holography, which I will discuss on the next slide. And the physical picture that they arrive at is very similar to what I'm going to talk about in this presentation. The other review article is from about 10 or 12 years ago, and it's by Samir Mathur. And in that review article, which is very pedagogical, he introduces the formulation of the black hole information paradox from an entanglement perspective. And I believe that's, to me, the clearest, conceptually clearest way to formulate the paradox. And as a test of the solution that I propose today, I'm going to go through Mathur's construction, which is called Mathur's theorem, and show how our solution evades the problem that Mathur first pointed out. Now, on this slide, I'm giving a quick overview for impatient experts. So if you've worked on things like ADS-CFT or holography, or you already know about the black hole information problem, this is for you. If you're not an expert, just ignore what I'm about to say. It's not necessary to understand to get the rest of the talk. So you may be familiar with the concept of ADS duality. I'll define that here as a bulk theory with gravity, which is dual to a boundary theory, which may be a gauge theory or a conformal field theory, but which doesn't have gravity. And generally, it's believed that the gauge theory or the conformal field theory will have unitary dynamics. So if I have a black hole in the bulk, which evaporates, it must be dual to some unitary process on the boundary. And therefore, the black hole evaporation must somehow be unitary also. And because ADS-CFT is now over 20 years old, people have sort of felt since the introduction of ADS-CFT that there must be some resolution of the black hole information problem. Secondly, I want to introduce the concept of information holography. So that is distinct from ADS duality. So information holography says that the quantum state of bulk configuration, so for example, a black hole in the bulk, can be determined from measurements, say, of correlation functions at the boundary of space-time. So it's not a dynamical duality between the bulk and the boundary. It's a statement about what aspects of the quantum state of bulk configurations can be measured, can be determined from measurements at the asymptotic boundary. And this progress in information holography, as I mentioned, a lot of that has been due to Surat Raju and his group. And what's interesting is both A and B suggest that black holes must evaporate in a unitary way. B even goes so far as to imply the existence of quantum hair. So in order for B to be true, there must be something like the quantum hair I'm going to talk about today. However, what I want to point out is that neither A nor B reveals how information that's in the black hole actually gets encoded in Hawking radiation. And today I will present explicit expressions which show you how the information is encoded in Hawking radiation. So that was kind of for experts. Now I'll come back to a more elementary introduction. So the black hole information problem has been an open problem since it was formulated by Hawking in 1976. And we do not have a complete short distance theory of quantum gravity. However, what I'm going to argue today is that we can resolve the paradox. We can both formulate the paradox as it was originally formulated, and we can resolve it through long wavelength properties of quantum gravity, in particular by looking more carefully at the quantum state of the graviton field outside a black hole. And in this hierarchy of theories that I have presented at the bottom of the slide, already in Newtonian gravity, you could see some hints that black holes must exist. Once you have general relativity, you can find specific classical solutions in field theory that describe black hole spacetimes. What Hawking did was calculate the propagation of quantum fields in a curved background spacetime. And from that, he concluded black holes must evaporate. And that immediately then suggested a paradox because it wasn't clear at all how the information behind the horizon of a black hole could get into the Hawking radiation. And today, what I'm going to do is go one step further, which is that I'm going to consider the quantum state of the graviton field, which is produced by a compact source. And once we understand that quantum state, we can resolve the paradox. Okay, so let me remind you of something called the No Hair Theorem. So one can classify all the external metrics of classical black hole solutions. And there's a theorem which is called the No Hair Theorem. John Wheeler, the famous Princeton physicist, coined the term black hole. He actually originated the term black hole, and he also originated the phrase, black holes have no hair. And that refers to this classification, the classification that says that the external fields of the black hole, at least classically, are determined by certain conserved quantities, such as the mass of the black hole, its angular momentum, and its total charge. However, what I'm going to show today is that quantum gravitational effects actually violate the classical no hair theorems. There is something called quantum hair, and there's no reason why the no hair theorems have to apply once you quantize gravity. Okay, let me further review what is special about black holes. What is special about a black hole is the way that it modifies the causal structure of space-time. So if I have a classical solution of the Einstein equations, I can ask the question, what is its causal structure? And in this picture, we have light cones. And so if you have a particle at the vertex of the cone, the light cone describes the possible trajectories of a null particle, a particle which travels at the speed of light emitted from that point. And the important aspect of a black hole spacetime is that once you cross the horizon, the light cone at that point in the spacetime manifold tilts. It tilts so that a particle which is past the horizon can no longer reach future infinity. In fact, if you analyze the global trajectory of such particles, they must eventually terminate in the singularity. So once you have a black hole spacetime, you have bifurcated the causal structure of the manifold so that some points can escape to future infinity, but other points must reach the black hole singularity. Now, if you look at quantum fluctuations just outside the horizon, you can have the following thing happen. You could have a particle-antiparticle fluctuation with the quantum numbers of the vacuum state. And it could be the case that one of the pair falls through the horizon while the other partner of the pair escapes to positive infinity. And the partner in the pair that reaches positive infinity, future infinity, is a Hawking radiation quantum, whereas the one that falls in has negative energy and it reduces the total energy of the black hole. Now, two phenomenological aspects of Hawking radiation: the temperatures are quite low. They're proportional to 1 over the radius of the black hole in Planck units. So for a macroscopic black hole, this temperature is extremely low. The radiation is an extremely long wavelength phenomenon. In fact, the relevant length scale is the Schwarzschild radius of the black hole. And the lifetime of the black hole is very long. It's proportional to the mass of the black hole cubed in Planck units. So we're talking about a very slow, semi-classical, long wavelength phenomenon. Now here I've drawn a Penrose diagram which emphasizes the causal structure of the black hole spacetime. And here we've depicted a black hole which evaporates. This is not an eternal black hole. This is a black hole which is going to at some point cease to exist. And I want to remind you that light-like trajectories in the space-time travel at 45-degree angles. So you can have particles which come in from past infinity and reach the horizon. You can also have, for example, photons, which are emitted by the star here, which collapses to form the black hole. And these photons can reach future null infinity. So now I want to call your attention to this dotted line, which is the world line of an external observer. And at point A, the observer can receive photons that came from the star, and the black hole has not yet formed. So observer A sees the star. If you follow that observer forward in time to the point B, he can now see Hawking radiation, which originates just outside the horizon, and he can see that there's a black hole. And if you go a little bit further into the future of the space-time to point C, that observer can see that the black hole has fully evaporated and there is no black hole left. And the problem which was pointed out by Hawking in 1976 is that black holes seem to violate unitarity. If I start with a pure state describing the universe, describing the star and the vacuum outside the star at early times, that pure state seems to evolve into a mixed state at late times. And as we know, quantum mechanics, as usually formulated, is unitary. Pure states should not evolve into mixed states if we take into account all degrees of freedom in the universe. Okay, so in this diagram now, I've drawn what are called nice slices. So in general relativity, one can choose the coordinates so that all of the points that are on each of these individual blue lines can be considered simultaneous. They can be considered as happening at exactly the same moment in time in the chosen coordinate system. So you can think of the progression of this foliation of the space-time from nice slice to nice slice to nice slice to nice slice as the progression in time. Now, one early formulation that goes back to the 1990s of the Hawking paradox is to consider this last nice slice that I'm indicating here. And that slice is chosen so that it intersects almost all of the Hawking radiation that's produced by the black hole, but it also intersects all the matter that fell into the black hole. And by the no cloning theorem, the quantum state, which represents the matter configuration here, cannot also be reproduced in the Hawking radiation. So the no cloning theorem combined with the fact that I can construct this nice slice, which exists, which is space-like and exists at a moment in time, suggests that there is a paradox, that I cannot, the quantum information that is here cannot also be here. And if it cannot be here, it cannot be in the Hawking radiation. So that is another formulation which is based on the causal properties of the space-time of the paradox. Now, these formulations of the information paradox assume a fixed classical background geometry. So we don't, at least in the early formulations of the paradox, consider that the geometry itself is quantum mechanical and has quantum fluctuations. So when you consider those quantum fluctuations, it turns out the causal structure and the localization of information are much more complex than I've described in the slides earlier. In fact, what we're going to discuss today is that the quantum state of the graviton field outside the horizon depends explicitly on the internal quantum state of the black hole. Now, nothing I've said up till now says anything one way or the other about this possibility, because up till now, we've always treated the gravitational field as a classical background geometry, and we've not talked about its quantum state. Okay, so in the next two slides, I'm going to summarize the results of the first of the two papers that we wrote. This is the one that was published in Physical Review Letters. And the first main conclusion is that the asymptotic graviton state of an energy eigenstate source is determined at leading order by the energy eigenvalue. So the question we're trying to ask is, I have a compact source, it's a fully quantum mechanical object, and it has an associated graviton field that it is the source of. And we are asking questions about the quantum state of the graviton field and how is it related to the quantum state of the compact object. This is a very different question than we normally confront in classical general relativity. In classical general relativity, we take the compact source to be described by a semi-classical T mu nu stress energy tensor, and then that determines a classical space-time geometry. Here we want to ask about a quantum mechanical compact source and the quantum state of its graviton field. Now, it turns out it is the energy eigenvalue of this source that determines the long-range quantum state of the graviton field. And this immediately tells you that if there are no accidental degeneracies, so if I think of my compact source as a many-body system, if there are no accidental energy degeneracies, there is a one-to-one mapping between the graviton states and the matter source states, because the matter source states have different energies and each energy corresponds to a slightly different graviton state. If I build a semi-classical matter source out of the individual energy eigenstates, I have to superpose different energy eigenstates, and then I get a superposition of gravitational states. And I'll discuss this in more detail in the next few slides. The second main conclusion of the first paper, of the Physical Review Letters paper, is that if you allow quantum gravitational fluctuations, so for example, you allow quantum loops of gravitons, you can compute the corrections of those quantum fluctuations to the long-range potential of a compact source. And you can show that there are 1 over r to the 5th potentials, and the coefficients of those potentials depend on the internal state of the source. This calculation is done in effective field theory, and I'll review the calculation again in subsequent slides. This provides an explicit example of quantum hair, of how the graviton quantum state, which corresponds to different values of the semi-classical potential, encodes information about the internal state of the compact object. In this case, the compact object we study is a dust ball. And it turns out that if you take two dust balls that have exactly the same mass, but they have different density profiles, integrals over the density profiles determine the coefficient of r to the -5. So you get different quantum corrections to the long-range potential depending on the internal state of the compact object. Okay, so coming back to point 1, we said that a compact source, which is an energy eigenstate with energy eigenvalue E then uniquely determines the quantum state of the associated graviton field. And it turns out this result is actually familiar if you've ever studied the constrained quantization of QED. So in QED, you have a Gauss law constraint, and you can construct in constrained quantization the exact ground state of the photon field in the presence of a charge Q. So the source has charge capital Q, and you can build this as a coherent state with the charge appearing explicitly here in the exponent. This vacuum state is the vacuum state with zero charge. Little q is a Fourier transform of the Coulomb potential, and B dagger of K is a linear combination of creation operators of the non-propagating photon field. So a linear combination of the temporal and longitudinal components of the photon field, depending on your choice of gauge. So it turns out is a known result. Now, it turns out you can repeat the same constrained quantization now for gravity, and you get exactly the same result, except that this charge capital Q is replaced by the energy eigenvalue E of the compact source. So we can write the quantum state of the graviton field of an energy eigenstate source in this form, where I just replace the letter capital Q with capital E, and I replace the meaning of B dagger K. Instead of being non-propagating components of the photon field, they become non-propagating components of the graviton field. And it turns out that result, the result for gravity, even was known for in some very esoteric papers. Okay, so as I said, in both gauge theory and gravity, the asymptotic state is determined through the Gauss law constraint and how it affects constrained quantization. Another way to derive this result for the gravitational field is to look at the Schwarzschild metric and look at something called the double copy relationship. So recently, people have noticed that the tree level or perturbative properties of gravity are related to corresponding properties of QED. And that allows you to map the form of the coherent state on the previous slide into the gravitational coherent state, where you replace Q with the energy. So it turns out this is a known result. What's important about this result is that it shows the relationship between the quantum state or the energy eigenstate of the compact source and the quantum state of the gravitational field. Okay, so I'm going to use the notation psi g of E. So psi g means the quantum state of the gravity field, and it is a function of E, where E is the energy eigenvalue of the source. A semi-classical matter configuration is a superposition of energy eigenstates, and generally will have support in a narrow band of energies. So these coefficients C sub n will have support only in some narrow band, and a semi-classical state like psi on the left here is written as a superposition of energy eigenstates psi n. But then if I write the corresponding graviton state, it is an entangled superposition of individual coherent states of the type that I described earlier. Okay, so let me summarize in more physical language what I just said in the last 5 slides or so. So if I have a complicated object, let's suppose this is a baryon. So it's a bound state of quarks, but inside are not only the 3 valence quarks, but there are fluctuations of glue, the gluonic field. There are also fluctuations of quark-antiquark pairs. So this object, this baryon, is itself really complicated. How does a long wavelength photon couple to a baryon? Well, we know in low energy effective field theory, its main coupling is to the total charge of the baryon. That is how the photon couples to it. Now let's consider I have propagating in time a compact matter source. That matter source could be a complex many-body system with many energy eigenvalues. How does a long wavelength graviton couple to that object? It turns out it couples to the energy eigenvalue of the compact object. And it's completely an analogy to the case of the baryon. And furthermore, when I want to write out the quantum state of the graviton field, I get this complex superposition state of this form. So that's a kind of effective field theory summary of what I just described in the previous slides. Okay, let me come to this second calculation that we did in the paper. And here, as I mentioned, we actually calculate explicit quantum effects from loops of gravitons and loops of other massless particles. So the effective action that I've written here was first worked out in the 1980s, but it took many, many years before people could figure out how to actually do physical calculations using this effective action. So this is an effective action, which is an expansion in curvature in R, and it's also an expansion in powers of G in terms of the length scale in Planck units. And these coefficients C1, C2, and C3 have divergent contributions. So C1, C2, and C3 are sensitive to the UV completion of the theory. However, these non-local terms, which have coefficients alpha, beta, and gamma, they are finite. So they are not sensitive to the short distance physics. And the results that we derive all result from alpha, beta, and gamma, and not from C1, C2, and C3. So they're insensitive to the UV completion. The effects that we're talking about are calculable in effective field theory. Okay. So we start with this effective action and we use it to compute modified Einstein equations. And then we use those modified Einstein equations to compute corrections to the external metric or the potential of a compact object. And we find, as I mentioned, a leading order 1 over r to the 5th corrections. And what that means is that if you have two, we did this in the context of dust balls, if you have two different dust balls, but the total mass of the dust balls is fixed, so they all have the same mass. However, the mass is distributed differently inside the sphere. You can get different coefficients for this r to the -5th potential. So this gives you another example of quantum hair, of a situation where when you turn on quantum mechanics of the graviton field, you see that there can be hints of the internal state of the compact source in terms of quantum properties of the external field. So although this is an effective field theory calculation, and r to the -5th is written as a classical potential, the r to the -5th itself, if you can think of it as a perturbation to the structure of the space-time or the geometry outside the complex object, and it's a quantum correction. So you have a quantum fluctuation in the geometry corresponding to the internal structure of the compact object. So it's yet another example of quantum hair. Okay, so now I'm going to assume that quantum hair exists outside a black hole. And what I'm going to do is show you how it allows the black hole to evaporate in a unitary way. And in the next few slides, I'm going to go very carefully through the evaporation of the black hole. Everything I'm doing here in the next few slides is very conceptually simple, but it's just a matter of defining all the terms and keeping track of all the complex things that happen during the evaporation. But it's not conceptually difficult. It's basically just simple quantum mechanics, okay? So let's assume for convenience that the black hole just emits one quantum at a time. And let's suppose that it emits exactly capital N quanta before it's completely gone. So the last quanta that comes out is called R sub n. Now, the symbols R sub I stand in for all the different quantum numbers of the Hawking quanta. So delta I is the energy, pi is the momentum, si is the spin, qi is the charge. But for simplicity, we're just going to write a particular radiation state in terms of R1 through Rn, because there's just too many symbols here to keep track of. So R1 through Rn stands for all of these values for each of the quanta. Now, we want to define an amplitude, alpha. Alpha is a function of E, the energy eigenstate, eigenvalue of the black hole, and R sub I, which are the quantum numbers of the ith quantum that's emitted. Okay, so it's the amplitude to emit quantum Ri from the exterior metric state psi g of E. So this E is the same as this E, and this Ri is the same as this Ri. Okay. Now, at leading order, we know what these alphas are. They're the Hawking amplitudes for a black hole of mass E. Okay, so let me make some remarks about alpha. So it's been known since Hawking did his calculation that there would be subleading corrections to his semi-classical approximation. Those could either be of the form s to the minus k, where s is the black hole entropy, or they could be exponentially small in the black hole entropy. And it was expected even then that these small corrections would exist. It's just that people didn't realize that such small corrections could actually help unitarize the black hole evaporation. Now, the main point that we're making here is that once you see that there is actually quantum hair, that the external quantum state of the black hole geometry is dependent on E, the internal quantum numbers of the black hole, that means that this amplitude can depend on E as well as Ri. So that is beyond the Hawking approximation. And it's that change in the analysis that allows the unitary evaporation to happen. Now, point 3 is a note to the experts. So if I take a density matrix description of the radiation, in the Hawking approximation, the radiation appears to be maximally mixed. However, it's been known for about 10 years that if you allow for even exponentially small, so the smallest possible corrections that were already expected a priori to the Hawking results, if you're allowed to place e to the minus s corrections in the radiation density matrix, because the dimensionality of the radiation space is so large, it's exponential in s in dimensionality, it's possible to modify rho, even though the leading order approximation to rho is maximally mixed. If you are allowed to include corrections even of this size, you can modify rho such that trace rho squared equals 1. So it is possible that corrections that are even this small can unitarize the density matrix, and that's been known for some time. Okay, so let me now walk through the full evaporation of the black hole. So G of En here stands for the quantum state describing the external graviton field, and that depends on En, the energy eigenstate of the black hole. It's a classic, semi-classical black hole. So a semi-classical black hole is a superposition of energy eigenstates, and these CNs have some support in some narrow range of energies. So if a classical, big semi-classical observer were to come and try to measure the energy of the black hole, they would get some energy which is in that band, that uncertainty band, where the CNs have their support. Now let's look at the emission of the first quantum, so R1. So the black hole now is going to emit its first Hawking quantum, which has quantum numbers R1. The final state includes R1, but it includes a different external state for the gravitational field because the energy of the black hole is now decreased by delta 1. So we have G of En minus delta 1 as the argument here. The amplitude to emit the quantum R1 from the energy eigenstate En is given by alpha. And then these coefficients Cn just go along for the ride here. So I sum over all possible quanta that can be emitted. I sum over the n's. That's a carryover from the first expression. And so this is the expression for the quantum state of the exterior of the black hole after the first quantum has now been emitted. Okay, so again, in this notation, G refers to the exterior geometry, R1 refers to the quantum numbers of the radiation. And we can just continue this way. So now I'm going to emit another quantum, R2. So I have to sum over all possible R2s. The CNs are still here. I get another amplitude. This is an amplitude for the black hole in state En minus delta 1 to emit quantum R2. And the state is now again modified external quantum state of the graviton field, where I subtract both delta 1 and delta 2. And in this state, I have both radiation quanta R1 and R2. Okay, so I can just proceed through this n times. And what do I get? At the end, I get a sum over all possible R1 through Rn, so all possible states of the quanta that could have been emitted. I get a product of each of these amplitudes, the argument of each amplitude keeps getting downshifted by delta 1, delta 2, delta 3. And the final state ultimately has no geometry because the space-time is approximately flat, but I have the full quantum state of all the Hawking quanta that have been emitted here. Okay, so if you look at this, this is a clearly unitary evolution where the precise information about the initial state of the black hole is described originally by these CNs, but these CNs actually are present in the final state. And if in principle, I could compute these alphas, so these are potentially known functions. And so if I knew the final state of the radiation R1 through Rn, and I compute these product of alphas, I can go backwards to infer what these values of CNs are. And so I can reconstruct the original quantum state of the black hole. And that's clear since this process was completely unitary. Okay, so here I've just written the final radiation state again. And again, we omit any reference to the geometry here now because the black hole is gone and we basically just have some quanta propagating in approximately flat space. There's no horizon anymore. The final radiation state is a complex superposition, and it depends linearly on the original black hole state through these CNs. And if you time reverse this process, you just go backwards in time, you will go all the way back to the original state of the black hole psi I, which is described by these CNs. So the time reversal invariance, which looks like a problem when you do the nice slice analysis, it doesn't seem like there's enough information at future infinity, future null infinity, to evolve all the way back into the star, which became the black hole. Here you can see that actually one can actually time reverse this entire process. Okay, now what I just did, I think, was not conceptually hard. It was just a matter of accounting or bookkeeping. What I'm going to say now is a little bit less conceptually trivial. Okay, so consider all the possible different radiation patterns R1 through Rn. Now, it turns out each of these patterns corresponds to a different recoil trajectory of the black hole. So every time the black hole emits a Hawking quantum, it recoils a little bit. And the entire mass, the entire rest mass of the black hole is eventually converted into Hawking radiation. So there are really many, exponentially many different trajectories of the black hole as it emits the Hawking quanta. The uncertainty in the final center of mass coordinate of the black hole, you can calculate it, and it's of order m squared. So if the black hole is of size m, the final position of the Planck-sized black hole as it emits its last quantum, that uncertainty is very, very large compared to the original size of the large black hole. So there's quite a lot of different things that could have happened, different trajectories that the black hole could have followed, and those correspond to different radiation patterns, R1 through Rn. And here we see that there are actually many different background spacetimes, which correspond to different coordinate transformations to go to the Penrose diagram, and they correspond to different radiation patterns. So this conclusion is not making any special assumptions about the nature of the emission amplitudes. It's already implied by the leading order Hawking rate calculation. So the leading order Hawking calculation says that there's roughly a thermal distribution of R1 through Rn. But if you think about all the possible thermal distribution, things that can result from thermal distribution of R1 through Rn, you get many, many different macroscopically different black hole recoil trajectories. And therefore you get many different semi-classical space-time geometries associated with the evaporation. So this is a little bit hard for some people to follow. Okay, so now here I've drawn some very simple pictures. Here you see there in this radiation pattern, there's a little bit more radiation emitted in this direction than anywhere else. That causes a net recoil trajectory of the velocity of the black hole like this. In this picture, a little bit more radiation has been emitted in this direction that causes the black hole to evaporate like this. In the set of amplitudes that are described in the expressions that I showed you a couple slides ago are all possible trajectories of this type. one in which the black hole does this, another where the black hole does this, and all of those appear as a superposition in the amplitudes that I wrote down. So distinct coarse-grained radiation energy densities imply different black hole recoil trajectories. That means that although in the past we just tended to try to describe this whole problem in terms of one Penrose diagram, we now see there are actually many different Penrose diagrams which are relevant to the evaporation. And there are many different nice slices that one has to make. You can see that just by thinking of where the center of mass coordinate of the black hole is at different points in its evaporation. It could be in radically different positions, and that means the origin of the Penrose diagram coordinate system is different depending on which radiation pattern we're talking about. So you end up with distinct space-time geometries. And this is a point that I think is largely overlooked in the black hole information problem. Okay. So what I'm going to do now is go back to Matour's formulation. This is the entanglement entropy formulation of the paradox. I'm going to show why the solution that we just described actually evades Matour's formulation. So let's go back to this picture where we have fluctuations just outside the horizon. And what Matour points out is that if you have a very big black hole, the region, the space-time region near the horizon is not very special. A freely falling observer will think that modulo some very small tidal forces, that it looks just like the ordinary Minkowski vacuum. And therefore, you know the distribution of all of these vacuum fluctuations from which the Hawking radiation comes. And so what Matour pointed out is that it's always the case that the quantum state of the pair, the partner in the pair that makes it to infinity, is highly entangled with the quantum state of its partner that falls into the black hole. So you can schematically write the state of the fluctuations that give you Hawking radiation as a highly entangled superposition of the mode that fell in, which he calls E1, which he calls E, with the mode that got out, which he calls B. And you always get this kind of characteristic form where the state of E is correlated with the state of B, another state of E is correlated with another state of B, and they're highly entangled. And the problem is that at the end of the day, you lose track of the E modes. You're forced to trace over the E modes because you don't have access to them. They end up in the singularity, and then you end up with a very high entanglement entropy. Okay. So as I said, you have an inertial frame near the horizon. You're going to discuss a bunch of modes for each Hawking event, B1 through Bn. Those are the Hawking modes. E1 through En are the partners of the Hawking modes, and those are the ones that fall into the black hole. Okay. And the vacuum fluctuation always has a schematic form, which is highly entangled, where if you know the state of E1, then you know the state of B1, et cetera. Okay. And if you just emit one quantum and I force you to trace over E1, then the entanglement entropy you get is log 2. Okay. Now, what Matour points out is that the black hole evaporates very slowly. One Hawking quantum comes out. There's plenty of time for the vacuum to settle back down into its ground state or close to its ground state. There's a fluctuation again, which produces a Hawking quantum. But at each one of those emissions, the state of the space-time just outside the horizon is always a highly entangled state. And it's always the case that the Hawking quantum that got out is highly entangled with something else, its partner that fell in. And so there's just no avoiding, according to Matour, a buildup of entanglement entropy if I lose track of all of the E degrees of freedom. Okay. Now, this particular factorized form of the wave function has to lead. If you force me to trace over these E degrees of freedom, the fact that this whole thing is factorized, it has this factorized form, forces the entanglement entropy to just keep growing and growing and growing the more Hawking radiation that I emit. And you'll notice right away that the expressions I wrote, the amplitudes that I wrote earlier with the alphas, those were not factorizable. They did not have this form. So now we're going to examine why is it that the expressions I wrote earlier do not look like this Matour form. And that's going to help us resolve the paradox. Okay. So as I said, because of this, factorized entangled form, if you omit n quanta, you're going to have to get n log 2 increase in entanglement entropy at the end when you trace over all the e's. And what Matour does in his theorem is he says, oh, if I allow small corrections to the Hawking evaporation, I can't really qualitatively change this result. I can maybe modify the rate at which entanglement entropy increases, but as long as these epsilons are small, as long as there are only semi-classical corrections, small corrections to the semi-classical result, then I still get a buildup of entanglement entropy, and so I always have a paradox. Okay, now the problem is that Matour's analysis is itself confined to a particular semi-classical nice slice. It's confined to a particular choice of background geometry. Okay, so his radiation patterns B1 through Bn and B1 prime, B2 prime, Bn prime, if these two patterns are sufficiently different, then they actually correspond to different background geometries. And therefore, for example, the E modes, which are defined as excitations, they're defined as little excitations at the horizon, just outside the horizon of a particular black hole as it evaporates. Well, you can see that there are actually more than one type of E mode. So if you look at the E3 mode, the third mode that fell into the black hole and corresponded to the third Hawking quantum that got out, there are actually many different E3 modes because even the position of the horizon is in different places during the evaporation. So his calculation does not take into account different copies of his factorized states, which themselves could have entanglements between them. So his factorized state might be entangled by epsilon with a large number of other factorized states that are happening in a different geometrical background. And that's the missing factor in his description and really all the traditional formulations of the black hole information problem. But all of those different possibilities are actually included in the amplitudes that I wrote down earlier. Okay, so his B modes, which make it to infinity, are what we called R modes. We did not have E modes in our description. What we described instead was the effect of the E mode after it falls in on the black hole state. The black hole energy, for example, the energy eigenvalue has to shift down by delta. And then the corresponding external state of the metric field has to then shift to be G of E minus delta. And so the analog of his entangled state, so he says, oh, if you know the state of EI, that tells you the state of BI, and therefore there's this entanglement. In our case, the entanglement is between a corresponding effect of E on the black hole and then on the external graviton state, and then one possible state of the Hawking emission, and then another possible state of the Hawking emission. So if you look carefully at the amplitudes that I wrote down, I think I reproduce it here on the next slide. This is just that slide where I've gone through this slide already, where I step through all the emissions. So the point is, if you look at this expression, this last line, it's sufficiently complicated that it actually contains many different copies of the Matour factorized state, but it also includes entanglements between those factorized states, if you actually look at this carefully. So the loophole in his formulation is that he is only tracking the set of excitations that are relevant to one fixed semi-classical spacetime, and he's neglecting correlations across different macroscopic geometries. That's the difference between our expression and his original formulation of the paradox. Okay, so that part is the part that people have the most trouble with. So I'm happy to ask any questions either now or at the end of the talk. I'm almost done, so you can ask lots of questions after I finish. So let me make a slightly esoteric comment on this. So there's something called the phenomenon of concentration of measure, and that happens in high dimensional geometry. So if you look at spheres in high number of dimensions, there's a phenomenon called concentration of measure, and this is very prominent in high dimensional geometry and mathematics. But it actually has applications in quantum mechanics, and it turns out all of quantum statistical mechanics, people have realized in the last 10 or 15 years, can be derived from this concentration of measure property, which is very powerful. So let's imagine that you have a very large Hilbert space, which I'm going to call Y. And let's suppose you have a small subset of that Hilbert space, which I'm going to call X. And in our case, Y is going to be the set of all possible final states of the radiation. And X is going to be a subset of all those radiation patterns, but only the subset which is consistent with one fixed geometry, one fixed trajectory of the black hole. Okay, so X is a small subset. There are many subsets X inside Y. What the concentration of measure result says, and a particular realization of it is something called Levy's lemma, which is very famous in probability theory or high dimensional geometry. Levy's lemma says that if I take a pure state psi in the large Hilbert space Y, but then I compute the density matrix on X, which results when I trace over everything in Y except X. Okay, so I trace over Y, the complement of X in Y, and that gives me this density matrix rho. It turns out rho is nearly maximally mixed. So this may seem very abstract to you, but this explains why if you do Hawking's original calculation or you try to formulate the paradox on one fixed subgeometry of all the possible geometries that can appear in this evaporation process, you will always find a very mixed state. But it's because you traced over very small entanglements across different X's, which actually unitarize the whole thing. And it could be the case that the original state, the actual final state psi is a pure state, but it looks to you like a very highly mixed state because you are only looking at one, you're conditioning on consistency with one specific space-time geometry. Okay, so here I say this again, entanglement between different X and X prime, so two different space-time geometries, or equivalently between different branches of the wave function psi, is neglected when you do that trace. And so therefore you get a mixed state, even though the actual state psi is a pure state. And in a way, this is a very, very compressed way of expressing what the Hawking paradox is all about and how it's resolved. So this is just the final state that we gave earlier. And if you look carefully at this final state, you'll see that it includes many X prime entanglements. It entangles different radiation patterns, which correspond to different macroscopic spacetime geometries. It does not factorize over those semi-classical spacetimes. And that's why it's unitary and it leads to a pure final state. Even though anybody who looks at it from just one sub perspective of say X or X prime thinks that it looks like a maximally mixed state. Okay, you could ask me more questions about this if what I said is confusing. Okay, let me conclude now. So classical no hair theorems do not extend to the quantum realm. In fact, the situation is actually the exact opposite in the quantum realm. Instead of saying there's only a limited amount of information about the black hole which can be recovered from the classical external field of the black hole spacetime, in quantum mechanics, you can recover all the information. You can actually uniquely determine the internal quantum state of the black hole if you're able to actually fully measure the quantum state of the graviton field. And we deduce this result in long wavelength quantum gravity. So we're not making any assumptions about string theory or short distance quantum gravity to come to this conclusion. So once you realize that this quantum hair exists, you can then very straightforwardly describe unitary black hole evaporation. You just have to allow for the fact that each emission amplitude is influenced by the quantum state of the graviton field. And once you track that through, you get a unitary expression for the final radiation state. And again, we've not invoked any exotic new physics. This is all expected physics from long wavelength, low energy quantum gravity. So the standard formulations of the information paradox, why are they wrong? They're wrong because they are only examining a small subset of the evaporation Hilbert space. They always condition on looking at a particular set of radiation quanta, which are consistent with some semi-classical space-time background, but there are actually many semi-classical space-time backgrounds which arise in the evaporation of the black hole. And if you do a fully quantum mechanical treatment, you will see all of them. So let me stop there, and I'm happy to take questions.
Thank you, Steve. Is there any question from the audience? Maybe I'll start with asking one question. I think, well, I mean, in how to put this, is the long range graviton essentially, as you say, it depends on the internal structure of the black hole. Is that right?
Yes.
Right. So I can understand this in the case of a ordinary compact source, which is not a black hole. But for a black hole, maybe I'm thinking about this too classically. But for a black hole, as you mentioned at the beginning of your talk, the causal structure is kind of important, right? So when I think about a quantum state inside a black hole, it always bothers me where that source is supposed to be located, because then it seems to be involving some retro causality because time is flowing toward the singularity. So there's some kind of backwards in time causation or something like that.
Yes.
Is that a worry, or am I thinking of this in the wrong way?
Well, okay, all of our intuition up till now comes from first imposing the classical geometry. So we like general relativity. That's the first thing we learn. We learn all about general relativity before we learn anything about quantum gravity, right? So we first find the classical solution, and then we develop intuition about the causal structure of that space-time, okay? So that's why it feels very strange to us to think that some influence from inside the horizon here can have any effect outside here, okay? But in a way, we're kind of like doing things in a certain order that don't commute, okay? So we first kind of very strongly impose classical physics, and then we ask about quantum fields propagating on that fixed geometry, okay? But that is very different from trying to quantize long wavelength gravity. So imagine I have a black hole. It doesn't have to be, the compact object here could be a full-blown black hole. And I don't ask any questions specifically about what's really going on behind the horizon, but I just ask, if I try to quantize gravitons, which are, say, 10 kilometers away from this black hole, do I know how to do that? Well, it turns out I do know how to do that. And when I do it, I notice that the coherent state I get actually cares about the energy eigenvalue of this thing. So I'm not actually saying that there's an influence that comes from maybe some guy's playing the violin inside the black hole. And I'm not saying the guy playing the violin is influencing these long-range gravitons or Hawking quanta. What I'm saying is that if you shift the energy eigenstate of the black hole just slightly, just from one level to another, it very subtly affects the coherent state. So there's no avoiding that, actually, because surely we know how to take a source. It doesn't matter whether the source is a black hole or it's a rock. If I go far enough away, my description, my effective field theory description doesn't care, right? So the point is, this is a quantum consideration that we just neglected in the past because we got so used to just like, okay, now I have this geometry and I'm going to let quantum fields propagate in this geometry. But if you put quantum mechanics first and you just say, okay, I want a consistent theory of long-range gravitons, and I have a source, I don't care whether the source is a black hole or it's a rock. It appears that I can't quantize this theory and obey Gauss's law without this quantum state, this coherent state, depending on the energy eigenstate of the black hole, it turns out. And that's the only ingredient that's used to derive these amplitude expressions later on.
Okay. Right. Any other questions from the audience?
Yes. Can you hear me?
Yes.
Thank you for your a nice talk about this interesting result. So my question is regarding the connection of your derivation with a Massless consideration. So in Massless language, the particle Hawking particle, one of which is falling into a black hole, another is escape to infinity. So how do you translate this infalling particle into the black hole state? I mean, in this case, you are using energy. So of course, energy is conserved, so it's fine. But if there's no conserved charge, how do we do the translation?
Yes. So if you remember in when Hawking came along and said, "Hey, black holes evaporate," right? No one ever really worked out how the back reaction takes place. So we have a fixed space-time, and then we emit a quantum from the black hole. So we just say, oh, but energy is conserved, so the black hole has to lose this much energy, and it has to lose whatever charge was carried off by the quantum. But we never really actually worked out in detail what is going on in that back reaction process, right? It's actually never done, actually. So what Hawking really computes is like, in a sense, a steady state distribution of radiation that's coming from a fixed mass black hole, okay? So I don't have an explicit description of that either, but I impose, in the same way that we impose back reaction, which makes the black hole shrink, I impose that if I need to emit a radiation quantum with quantum numbers Ri, then there has to be a correction in the internal state of the black hole, probably because it ate the E mode, okay? But then the external field of the graviton knows about that change in the energy eigenvalue or maybe the charges, and then that's reflected in the next amplitude. So there's memory between emissions of individual Hawking quantum. It happens because of the same back reaction phenomenon that's been present all the way since Hawking concluded that the black hole can actually fully evaporate. That back reaction has been hidden there, but nobody ever really fully worked out how that back reaction works because it's quite complicated.
In relation to the last questions, I think when Shiwen mentioned the conserved charge, he probably also has in mind the soft hair proposal by Hawking later on. So maybe you can also elaborate on that. I mean, the distinction between the soft hair and the quantum hair in your talk.
Yeah, to be honest, I never understood how this soft hair of Strominger and Hawking actually solves the information paradox. So I don't think they ever really fully, correct me if I'm wrong, I think they never fully elaborated how that encodes information about the black hole internal state. In our case, these very elementary expressions show you how the thing which specifies the quantum state of the black hole, which is a pure state, are these CNs. And then if you can compute in principle these alphas, so these alphas are properties of physics, you can just compute them if you have infinitely powerful computers. Right. I can map a particular final state of the radiation back to these CNs. So here we're showing you kind of almost in a stupid, explicit way how to encode the information about the black hole in the final radiation state. But I don't think that was ever done with soft hair.
Okay.
Sorry, may I ask a follow-up question?
Yeah.
So in this case, the conserved charge that you can reconstruct is, of course, a black hole energy. But in general, not every information can be written in terms of some conserved charges. In that case, how do we reconstruct it using the information of these cascading radiations?
Yeah, very good. So let me first, just to make it simple, let's suppose there are no gauge charges. Okay, let's suppose I just have some scalar fields and they collapse to form a black hole and there's no charge. Okay, so just to make it simple. Okay. The question is, can I fully specify the quantum state of the black hole just by knowing these energy eigenstates and then superimposing them with some coefficients. And of course, this is a complete basis, right, for describing this compact system. So I can describe a pure state in terms of just these coefficients C sub n, and then I recover the coefficient C sub n at the end. So it isn't true that there's more information. So remember that the whole paradox is a pure state supposedly evolved into a mixed state. But in these expressions, the pure state evolved into another pure state, but the two pure states are related linearly, as they have to be in quantum mechanics. So I can recover this pure state from this pure state. It really just boils down to these coefficients C sub n. Did I lose you guys? Hello.
Oh, sorry, I'm just not getting the idea that these energy eigenstates can fully describe the system. I mean, how do I say? So, for example, we have let's say a scalar, like you said, scalar field collecting into a black hole. So the scalar fields can have different, let's say, angular configuration. Then those information cannot be encoded inside the energy eigenstates, right? So how do we, from the energy eigenstate, reconstruct the angular distribution of the original scalar field?
I think the question you're asking is basically just whether the energy eigenstates form a complete basis for the Hilbert space of the scalar fields, right?
Yes, exactly.
Yeah, but I think they do, right? I mean, that's a usual assumption we make, right? That if we have a Hermitian operator, the basis, the eigenstates of that operator form a complete basis. Now, what you might be saying is, okay, maybe there's some degeneracies. So maybe there are two energy eigenstates which are different. Like maybe one is spinning this way and the other one is spinning this way, but they have exactly the same energy. So that would be difficult to, if I just track the energy, I can't tell the difference between maybe it's spinning this way and maybe it's spinning this way. Okay, so it's not that the energy eigenstates are incomplete. They are a complete basis. It's just that there may be degeneracies. Okay, so the problem of how to resolve the degeneracies has to do with higher correlation functions of the graviton wave function, which I didn't present in this kind of simple picture. This is something Raju and his collaborators have looked at very carefully. So they looked at, if you're probing the correlation functions, all possible correlation functions computed in the graviton state outside the source, you can reconstruct, you can distinguish between, for example, two degenerate energy eigenstates. I don't know if that answers your question, but I think the question you're asking is more about degeneracies, not whether the energy eigenstate basis is complete, because it is complete.
Yeah, exactly.
Yeah, but the question is these degeneracies. Now the degeneracies have to do then with higher moments of the graviton wave function. So you're computing higher moments, like correlation functions in that wave function. But of course you can imagine the thing spinning this way and the thing spinning this way has a slightly different effect on the wave function of the graviton. And that's something that if you look at that physics reports by Raju, it's the kind of thing that they explore in more detail. But so in my simple notation, I don't have that, but basically the point is just, if you had a degeneracy here that you had to resolve, there actually are different states G of En for the two degenerate states, because the graviton state will just be slightly different.
Are there any other questions?
Can I ask one more question?
Yes.
Yes. Okay. So thank you very much for the nice talk. Maybe my question is a little bit related to Yuanjun's first question, but in a more specific manner. So in the first few slides, you show you considered a dust ball, and then you calculated the correction on the potential and showed that the coefficients of that potential depends on the internal structure of the dust ball. So my question is that, is it or do you have any idea to replace the dust ball with a real black hole with an event horizon and repeat all the calculations?
Yes, so that in this particular effective field theory calculation, we only did it with dust balls, and we could not follow the full evolution of the dust ball as it collapsed. So we looked at a progression of static dust balls in the paper. Subsequently, we've done time-dependent calculations where the radius of the dust ball is actually time-dependent, and we can follow it further. But we haven't done anything in which you can follow it all the way through after it forms a black hole and fully compute all these graviton, virtual graviton effects all the way through. So we have not done that.
Okay, I see. Thank you.
Maybe on the behalf of the beginning graduate students, let me ask about the non-local terms. How do they arise in the effective field theory?
Yeah, so that's a great question. So if you just do pure gravity and you have no matter, then the massless degree of freedom is the graviton loops themselves. But then if you have other massless degrees of freedom, you can have a loop. Like you could have a photon going in a loop and then graviton legs sticking out from that loop. So if you look carefully at the coefficients alpha, beta, and gamma, they have a dependence on the particle content of the massless particle content of the theory, as well as obviously the graviton itself.
Any other questions, especially from the students? Maybe let me ask one more question. Towards the end, you mentioned about the superpositions, for example, the location of black holes and all that. This sort of has the vibe of the many world interpretations, right? You have to take into account all the different branches. So is this sort of contingent to taking seriously the many world interpretations? And what if, for example, someone believes in Baryon mechanics, for example, how do they interpret that?
Yeah, this is a great question. So let me answer. I'm going to give you two different answers. Okay, answering slightly differently. Answering slightly different questions, but related questions. So if you're trying to answer whether black hole evolution is unitary, then you're entitled to just ask, what is the Schrodinger evolution of the initial black hole state? So I have an initial black hole state, and I just consider Schrodinger dynamics, and I just want to make sure that at the end I get something which depends linearly on these CNs. Okay, and that doesn't assume any interpretation of quantum mechanics. So usually we allow Schrodinger evolution in between, and then at the end we have to make some decision when we quote make a measurement what happens. Okay, so the paradox that Hawking advocated was not about measurement. It was actually about the ordinarily unitary evolution, the ordinarily Schrodinger evolution. And he said, hey, there's already a problem, because when you put in gravity, you don't even get the ordinary Schrodinger evolution. You get something non-unitary already at that level before you even consider making measurements. Does that make sense? So, the formulation of the paradox itself generally doesn't care about quantum measurement. You just say, hey, in my spin or inside my quantum computer, I just have everything evolving unitarily, and it's only at the end that we're going to fight about the meaning of measurement. Okay, and it's the same thing in the black hole information problem. We make a black hole, we let it evaporate, and then we ask, is that initial state evolving according to Schrodinger's equation into a pure final state or not? And we don't really argue about interpretation. So that's one answer to the question. You just ignore measurement and interpretation. Just ask, is the unitary dynamics there, or does gravity interfere with the unitary dynamics? And Hawking initially said, yes, it does, right? So, and we're saying, no, it doesn't, okay? Now, here's an interesting question. If you have studied foundations of quantum mechanics, you know that at the end, when the measurement happens, a pure state does evolve into a mixed state. Because the moment you do the measurement, the description of the system is now a mixed state. It has different probabilities of being found in different outcomes. Okay, so there is a connection between, if someone says to you, hey, it's really bad that black holes cause pure states to evolve into mixed states. Someone could say, oh, it's really bad. We're going to spend 40 years worrying about this, right? But then if someone comes to your office after you teach them first year graduate quantum mechanics, and they come in and they say, hey, I'm really worried because measurements supposedly cause a pure state to evolve into a mixed state. That seems very bad. And that's exactly what Everett said. Everett said pure states should never evolve into mixed states. Pure states should just keep evolving into pure states. And it only seems like they evolve into mixed states because we decohere, our brains decohere into different versions which saw different experimental outcomes. And that's what that's Everett's version of quantum mechanics, which I'll just give an advertisement, Feynman, Gell-Mann, Hawking, Schwinger, Weinberg, all the great physicists deeply understand this and appreciate that there's nothing wrong as far as they can tell with Everett's quantum mechanics. And it's kind of shocking to me that the physics community doesn't really understand this. But anyway, if you look on my blog, I have quotes from all of the famous theorists that I just mentioned talking about Everett quantum mechanics, and Everett quantum mechanics is the actual natural quantum mechanics. The other one, where you have non-unitary collapse of a wave function, is the crazy quantum mechanics, and only Bohr and some other people believed in that. So that's my position.
Okay. Well, in some sense, I do agree with you that the many worlds seems the simplest because you don't have any additional assumptions to the rules, like the collapse or whatever, right?
Yeah.
And also I do agree that the different branches of the wave functions, it seems that there are a lot of confusions in the literatures about information loss, exactly what we mean by unitarity. It seems that many authors have different interpretations. So that's partly why I asked the questions. What do we mean by unitarity?
If you look at any complicated system, in fact, I'll just advertise my own work from a year or two ago. You can prove using something called von Neumann's quantum ergodic theorem. There's a quantum ergodic theorem by von Neumann, which was proved in 1929. It's a very powerful result. It's related to this concentration of measure stuff that I talked about.
Right.
You can use von Neumann's quantum ergodic theorem to prove that any initial quantum state, under mild assumptions about the Hamiltonian, will evolve into a macroscopic superposition state. It's basically unavoidable. And the question of how you want to interpret that, or whether you think at the end a measurement will collapse that into one macroscopic state, that's fine, that's up to you. But if you just talk about Schrodinger dynamics of a sufficiently complicated system, you can prove that it will always evolve into a macroscopic superposition state. And that in the slide that I'm showing you on the screen, you just see that when a black hole evaporates, if you're treating everything purely quantum mechanically, you see that all those different possibilities are there. Eventually, what you measure is a different question. But in the description, the quantum description of a state evolving in a very high dimensional Hilbert space, you get a macroscopic superposition. There's no avoiding it.
Right. Great. Is there any other questions? If not, I think we can end the session today. Right. Okay, thank you, Steve, for giving a fantastic talk about black hole information paradox. And hopefully we can have more discussions in the future.
Yeah, my pleasure. I hope after COVID I can visit you someday.
Yeah, definitely.
I'm trying to turn off the recording, but let's see. I'm going to stop sharing, and then I'm going to stop recording.